Today we're going to round off our discussion of oxidation and reduction by talking about fuel cells and photovoltaic cells. Right, so a fuel cell is a device that converts the energy of a fuel into electrical energy. And so the example that I have shown here is a hydrogen-oxygen fuel cell, and these you may have heard of before because the output of this kind of fuel cell is just water vapor, so it doesn't contribute to any carbon emissions in our environment. So there's been a lot of talk about figuring out how to harness that power to make vehicles run and things like that. So what's happening here, again, is an oxidation and a reduction. So at the anode side of our fuel cell, which is over here on the left, we have hydrogen coming in, and then we have that being oxidized when it reacts with hydroxide that's in the paste that's in the middle of our fuel cell. And so the hydrogen gas actually loses electrons and becomes water when it reacts with that hydroxide ion, or the OH minus. Okay, and then on the other side, where our cathode is on the right side here, that is where we have water vapor and oxygen gas coming into our fuel cell, and they react to make more OH minus, and the oxygen is actually reduced in this case. So it goes from just O2 gas to the oxygen in the hydroxide ion. Okay, so in this particular example, there's a light bulb being lit up, but these fuel cells can be used for lots of different things. There are buses that run on hydrogen oxygen fuel cells, but getting the hydrogen is a little bit difficult, which is why these are not as used as regularly as maybe you might think. Because right now we still have to generate the hydrogen in order to put into the fuel cell, and that takes energy. So what I really want you to take away from this is that in this hydrogen-oxygen fuel cell, you have an oxidation and you have a reduction. The oxidation happens at the anode side, and the reduction happens at the cathode side. And hydrogen was oxidized, and oxygen is what is reduced. All right, now I just want to give you a brief introduction to photovoltaic cells, and these are what solar panels are made of. So this is something everyone should have heard of, but I doubt that most of you really understand how they work. So most photovoltaics are made from silicon, and silicon has 4 valence electrons, as you can see in the images down here. And so the way they make photovoltaics, so in order to generate electricity, we have to move electrons, right? This is what we learned when we did batteries in the last section. And so there are 2 different types of silicon that they use, and it depends on what they're doped with. So N-type silicon is doped with extra negative charge, and so in this case, that comes in the form of arsenic, and arsenic has 5 valence electrons, so there's essentially an extra electron floating around that's not quite sure where to go. Okay, in a P-type, a sample of P-type silicon, that the P is for positive, and so in that case we have actually missing electrons. So boron is what we've doped the silicon with over here on the right, and since it's missing a valence electron, it has what are sometimes referred to as holes, and so the electrons tend to want to move from N-type silicon to P-type silicon because there's extras in the N and there are holes in the P. So solar panels, or photovoltaics, rely on the photoelectric effect to work, and the photoelectric effect is the ability of light, in this case light from the sun, to knock electrons away from the atoms in an object. And so when sunlight hits an object, the electrons sometimes bounce off. Okay, so in a solar panel or a photovoltaic, we layer P-type and N-type silicon. And like I said, the N-type has extra electrons, and so when the light hits them, they tend to want to bounce off, and they end up in the P-type layer because there are holes there where there aren't electrons. Okay, so on the left is what we would start with, and then after the photoelectric effect causes some of those electrons to bounce around, then we shift over to what you see here on the right. And so you see a buildup of positive charge at the top because those there were some arsenic ions, arsenic atoms in there, and as they lose an electron, they're going to have a positive charge. And there's a buildup of negative charge on the bottom because those boron atoms, as they gain electrons, they're going to end up with more negative charge because electrons are negatively charged. Okay, so in order for this to work, we get a buildup of charge in the N-type and in the P-type layers of our photovoltaic. Right, so the way we harness this to generate electricity is that we attach a wire to both the N-type and the P-type layers of the photovoltaic. And so as the electrons want to move out of the N-type wafer, they continue through the wire up here above, through whatever we want to use to generate electricity, in this case a light bulb, and then back through the wire into the P-type, and then the electrons continue to travel in that direction because the electrons are attracted to the positive charge that we've built up in the N-type and the negative charge that's built up in the P-type. Okay, so we'll discuss this a little bit more in class and try to get a really firm handle on how the electrons are moving and how we can make predictions about how they move. But this wraps up our discussion of how we can generate electricity using different types of chemical reactions.